well, this is called Rodriguez formula, but you can think of this as a definition of the Legendre polynomials for integer, positive integer L, or L could be 0. If L is 0, you're going to get 1. And what I want to prove is that if you take the square of this and integrate from -1 to 1, you get this value. Now, why is that important? Well, what we're really trying to do is, as I explained before, you can think of inner products of two functions on an interval as integration from a to b of f of x times g of x dx. Now, sometimes you might have a weight functions put in here. Usually you want it to be positive. What that means is, what you're trying to do is you're taking PL and you're squaring it, which is like taking the dot product of a vector with itself, right? And you know what you get if you do a dot product of a vector with itself? What do you get? Dot product is the norm of the first times the norm of the second times cosine of the angle between. If you have the same vector, what's the angle between? 0. And cosine 0 is? 1. So this ends up being? Yeah, norm squared. Okay. And by the way, those of you who didn't get what I meant when I did this, this is just another way to write down the dot product in a more general setting. Okay? When we say dot product, it's usually in 3D or maybe 4D, and you have a fixed set of vectors which we call the standard unit vectors, right? And we define dot product as like, you first write down the coordinates and you multiply the coordinates, you add them up. That's dot product, but it doesn't have to be that. You can like just take all these properties of the dot product and make something called an inner product, and it will enjoy most of the things that you get here. Okay. All right. So that's what we're trying to do here. We want to know what the norm squared of this thing is. And because this result says the norm squared is this, what this is saying is that the upshot of this calculation is saying that PL x divided by square root of 2 over 2L plus 1 is going to be a unit vector. It's like a unit vector. Now, what I'm like not really going to prove, but essentially going to prove after this one is to show that if I have PL of x and PK of x with two different K and L, then these are orthogonal to each other. In other words, if you multiply them together, you integrate at 0. In other words, their dot product is 0. If their dot product is 0, then they're perpendicular, right? Yeah. So if it's perpendicular, then if you collect all of these, those are called orthogonal set. And if it spans the entire set of entire vector space, it's called the basis, orthogonal basis. And if you take each basis element and divide it by its size, you end up with something called an orthonormal basis. Right? And having an orthonormal basis allows you to take any other vector and express that vector as a linear combination of the orthonormal basis vectors very conveniently. Okay, so I'm going to try to say this again. After we talk about the more general thing. But for now, I'm just going to focus on proving this one. Okay. So what happens that usually when you try to show orthogonal, given that such and such functions arise from a Sturm-Liouville problem, that's easy. That's we can actually prove that in general. However, when you take an element and you try to calculate the norm, that's when you actually have to get your hands dirty, because it really depends on what your function is. There is no general theorem about being orthogonal. So, general theory about what that square should give you. Okay? So this is where you really don't have a nice way of doing things. So you're going to see that my proof looks pretty complicated, but I really can't help it. Right? Okay, so let's do this. All I'm going to do is I'm going to start from this side. And I'm just going to stick this in here. And if I stick this in here, these coefficients are the same, so I can take the square of this coefficient, move it outside the integral, and it's going to be 1 over 2 to the 2L, L factorial squared. And then we have Lth derivative of x squared minus 1 to the Lth power times Lth derivative of x squared minus 1 to the Lth power dx. Oh, where capital D means differentiation by dx, right? Where d means d dx, differentiate. Okay. And what you want to do is you just want to do integration by parts several times. So let me show you what integration by parts is. What is integration by parts? You have two functions multiplied. The integration by parts say it's a to b. You integrate just one of them, right? And then keep the other one unchanged. Right? But then in the next stage, what you already integrate, you keep, but the one that you did not integrate, you differentiate. Right? That's integration by parts, right? So that's what I'm going to do here. I'm going to integrate this. Integrating a derivative will get rid of one of the derivatives, right? So what's the antiderivative of this? The antiderivative of this would be? dl minus 1, because this is this thing differentiated L times, but now you differentiate one less time because you integrated it. Okay. And then in the next stage, this part was the one that we did not do anything to, right? So that, in the next stage, you get to differentiate. So what do I write here?
L plus 1.
L plus 1. I put a gigantic parenthesis here so I don't have to write this twice. Okay. Now, the thing is, because this is being differentiated, this to the nth power is being differentiated at most L minus 1 times. Even if you differentiate this, this is going to be a huge differentiation. But at the end of the day, you will see that you always get 1x squared minus 1 left. So this thing, it's a huge... We talked about the generic formula for nth derivative, right? Yeah, so this is a very big computation, but it happens that you get something, but everything will have x squared minus 1 as a factor. Okay? So when you plug in 1 or negative 1 to this, it's going to give you 0, because 1 squared minus 1 is 0, negative 1 squared minus 1 is 0. So this part is going to go away. Okay. So that's interesting. That means we can just keep doing this over and over again. We can again integrate this one and move, because that boundary term vanishes, you end up differentiating this more. And by the way, when you do analysis, if your job after completing your PhD in mathematics is mathematical analysis, then a lot of times your research will be involving doing the integration by parts. Okay? Integration by parts, either in this setting or even in multivariable setting. Sometimes integration by parts are called Green's second identity or something like that. And these things give you very powerful results. Okay? So we can just repeat this again and again and keep taking one of the derivatives away from here and you put it in here. Just keep doing that. Okay? So you do that, and at the end of the day, what you're going to get is you're going to get 1 over 2 to the 2L, L factorial. Oh, and by the way, every time you take that away, there's a negative 1, right? So at the end of the day, you're going to get negative 1 to the nth power multiplied, and you get x squared minus 1 to the nth power, and d 2L differentiate derivative of x squared minus 1 to the nth power. Okay.
There is a L time. Do this L time. L times.
What do you mean?
Do the repeat the process.
Yeah, we do the integration by parts now again and again and again. You keep taking away the derivative from here and you apply it to here. And you do this L times, so there's negative 1 to the nth power, right? Because there's a minus every time. Right? And then, because this 1 will eventually increase to L, L plus L gives you 2L, right? Okay.
Sorry, why does that become dl to the negative 1?
D, this L minus 1?
No, in the group. Yeah.
This one?
Yeah.
Whatever you integrated, you put it back.
It's fg minus f. Oh yeah.
Right. So whatever you integrated, you put it exactly in the same format.
Right.
Yeah. So. Okay. All right. So you might wonder, what does this achieve? It still looks cryptic, but here it achieves something. What is this? You see that if you expand this thing, the highest order is x to 2L, and then using binomial theorem, the next one would be L choose
So that's basically
1 x to 2L minus 2 plus something something. Yes?
it's 1.
Huh?
No, 1 is
Not 1.
2L factorial.
2L factorial. Yeah, exactly. See, everything that has less order than this one will eventually become what?
0.
0. If you have x squared and if you differentiate 3 times, what do you get? You get 0, right? X squared differentiates to 2x, 2x differentiates to 2, and the third time you differentiate 0. So if you're differentiating a polynomial, by the number of derivatives being more than the order of that polynomial, what do you get? So you get 0. They go away. Right? So the only survivor is would be this one. But what do you get if you differentiate x to the 2l times?
It becomes 1, isn't it?
No. When you differentiate, what do you get? 2l x to the 2l minus 1. Differentiate again, it's 2l times 2l minus 1.
Right.
X to the 2l minus 2. So keep doing that, eventually you get 2l factorial. Okay. So you're going to get 1 over 2 to the 2l, l factorial, negative 1 to the lth power, 2l factorial, and times integral of x squared minus 1 to the lth power of dx. Oh, forgot to say negative 1 to 1. Okay, so now how do we calculate this one? Well, how do we calculate that one? Again, integration by parts. But this time when you do the integration by parts, wait a minute, is there an easier way? No, I don't think so. It's not that easy. Okay. So for this one, I'm going to define I sub L as this integral value. Okay. Now I'm going to use the fact that, no, I don't have to use that. Sorry. I was about to use the even and oddness, but I guess I don't need to. So I'm going to apply integration by parts, but this time I'm going to integrate 1. So it's going to be x times x squared minus 1 to the lth power. Plug in 1 and negative 1. Again, you see that this is 0, right? And then minus negative 1 to 1 x times, now you have to, because this one I didn't do anything to it, in the next stage I have to differentiate it, right? So what do I get if I differentiate it? It's L times x squared minus 1 to the L minus 1
2x
times 2x. Okay.
still hard.
Yeah, it's still hard, but now something will come out of it, right? Okay, so first of all, 1 plugged in here is 0, negative 1 plugged in here is 0. So that's gone, right? So that's still gone. And this one, I'm going to rewrite this as, I'm going to pull the L and 2 outside, and then rewrite this as negative 2L x squared minus 1 to the lth power dx.
L minus 1.
L minus 1, thank you, that's important. That's important, okay. And then say, well, you know, x squared is x squared minus 1 plus 1, so I can rewrite this as negative 2L, negative 1 to 1, x squared minus 1, times x squared minus 1 to the L minus 1 plus 1 times x squared minus 1 L minus 1 dx. Okay? So do you agree with this? This is just algebra, right? If you factor out the x squared minus 1 to the L minus 1, you get x squared minus 1 plus 1, which is the same as this x squared, so it's the same thing, right? But then, look what this is. This is x squared minus 1 to the nth power, which is exactly IL, right? On the other hand, what is this one? This is, that we can call IL minus 1, right? So all this calculation gives you the following fact, that IL is equal to negative 2L IL minus 2L IL minus 1. Okay? Move this to the other side and you get IL times 1 plus 2L equals to negative 2L IL minus 1. And finally divide, you get IL equals to negative 2 over 1 plus 2L IL minus 1. Okay? So now,
Let's find LI1, right? Or I0.
oh, sorry, IL. Sorry, IL. Okay, now we can just repeat this over and over again to get the following. So IL is going to be negative 1 times 2L over 2L plus 1 IL minus 1, but that's going to be equals to negative 1 squared times 2L over 2L plus 1 times 2L minus 1 2L minus 1 times IL minus 2, right? You're just you're thinking of this as a recurrence relation, and you're just applying it over and over again. Or if you didn't get what I said, so eventually what I'm trying to say is that this is going to say negative 1 to the L will be, if you factor all the 2's out, it will be 2 to the nth power and then L factorial. And then if you...
It's 2L plus 1 factorial, double factorial.
Double factorial.
And it's L0.
I0. But I0 is what? I0 is integral from negative 1 to 1 of x squared minus 1 to the 0th power dx. So that's just 2.
Okay. Yeah.
So I0 is 2. So you can say this. Now if you didn't like this argument, we can do this. I still don't want to erase this. Well, yeah, this is here. So here's another way to see what I'm just saying. IL equals to negative 1 times 2L over 2L plus 1 IL minus 1. That's what I just showed, right? But although I made it sound like this L should be the same as this L, but this calculation was true for any L, right? So I can start by saying this is true when L is 1, right? So you can have I1 equals to negative 1 times 2 over 3 of I0, right? And you can plug in I2 equals to negative 1 times 4 over 5 I1, but then you stick this in here and you get negative 1 squared 4 times 2 over 5 times 3 I0. And you keep doing this over and over again, you'll see the pattern, which is exactly this one. Do you agree? Right? It's going to be the same thing, right? Okay. So plug in 3 and repeat the process. You'll eventually see that this is what you get. Okay, now what I want to say is that eventually, since I0 is 2, I have the value of IL that I want. This is our IL, right? So we can finish the calculation if I replace this square rectangular part by this thing and we're done. But that doesn't seem to achieve our goal, do we? Like, I want that complicated thing to be simplified as 2 over 2l plus 1. So we need to do a little bit more work here. So the way we are going to do the work is by rewriting this and say I have 2l plus 1 times 2l minus 1 times 2l minus 3 times all the way up till 3 times 1. I0 is 2. And then I'm going to stick in 2l here, 2l minus 2 here, everything here, top and bottom. Two and 1. So that this denominator looks like 2l plus 1 factorial. And what it does is this thing is exactly same as what we had before, right? So all it does is it just it gives you another of these 2 to the n to this 2 to the n, another one of l factorial. So on the top you get 2 to the n squared l factorial squared. Okay? So times 2. And that's what I'm going to now replace. All right? So now we go back here, continue this calculation. Sorry, that should have been a squared, I forgot. Okay? Somewhere along the calculation I forgot that squared. Okay, so I just put that in, negative 1 to the lth power, 2 to the lth, why did I put nth power, lth power? 2 to the 2lth, or 2 to the lth power squared, n factorial, the l factorial squared, over 2l plus 1 factorial times 2. This much was the calculation we just figured out. But then you see that these cancel. Negative 1 times negative 1 is positive 1. Positive 1 to the lth power is just 1, right? So you can say that these two cancel. And then these two cancel. And now you have 2l factorial divided by 2l plus 1 factorial. What's that? Everything cancels if you write out 2l factorial with 2l plus 1 factorial. The only thing that's left is 2l plus 1. You're right. And then there's a 2 there. So that's it. That's the calculation.
And show me again how to do
you want me to explain this again?
Yeah.
Okay. All right. So that's the proof. Let me just try to explain this yet one more time because you seem to have trouble. So I can just go back in here and talk about this one. You have equals to negative 1 squared 2l 2l minus 2, right? This is 2l minus 2, 2l minus 4, all the way up till 4 to 1 times il minus 2, I0, okay? In the denominator you have 2l plus 1 times 2l minus 1 times 2l minus 3, all the way up till 5, 3, 1. Okay? So what I'm going to do is I'm going to multiply 2l top and bottom so that 2l goes in here and this gets squared. Okay? I'm going to multiply 2l minus 2 top and bottom so that this gets squared. Multiply 2l minus 4 top and bottom so this is squared. And put in 4 and 2 there, so these are squared. And then you can see that the denominator becomes 2l plus 1 factorial. Okay?
Okay.
Agreed? Okay. Whereas on the top, you have, if you take 2 squares out from everything in here, you have L of those, so you have 2 squared to the lth power taken out, And if you take them out, you get L factorial squared times I0, and I0 is 2. That's why the end result is this one.